Problem 1. We're told that the nucleus in a typical atom has a radius of 10 femtometers. So we know that the nuclear radius is about 10 times 10 to the minus 15 meters. And an atom has a radius of 1 angstrom. So R for the atom is approximately 1 times 10 to the minus 10 meters. Now, part A asks us to calculate the volume of the nucleus. So the volume is equal to 4/3 pi the nuclear radius cubed. This is just the volume for a sphere, so we're just going to substitute into this equation. So this is 4/3 times pi times 10 to the minus 15, all cubed. And so solving this one on the calculator, we end up with 4 times 10 to the minus 42 meters cubed. So this is just to one significant figure because these values are only given to one significant figure. Now part B says calculate the volume of an atom. So we use the same equation now. We've got 4/3 pi, but now instead of the radius of the nucleus, we use the radius of the atom cubed. So this is 4/3 pi times 1 times 10 to the minus 10 all cubed, and solving that on the calculator we get 4 times 10 to the minus 30 meters cubed. And so part C then asks what fraction of the atomic volume is filled by the nucleus. So this is the volume of the nucleus, this is the volume of the atom. So what we will have is the volume of the nucleus over the volume of the atom, which is equal to 4 times 10 to the minus 42 over 4 times 10 to the minus 30. These 4's will cancel out and we'll end up with 10 to the minus 12 is the fraction of the atom which is filled by the nucleus, so a tiny part. So we can either leave our answer as 10 to the minus 12, or if you want to give it as a percentage, then you divide it by 100, so it would be 10 to the minus 14%. Part D then asks us, is it true that the atom is mainly empty space? Well, yes, because electrons don't take up any space, and you can see that this nucleus hardly takes up any space, so almost all of the atom is actually empty space. Problem 2. In this problem we have a graph showing the binding energy per nucleon. So this is the amount of energy which is released when these nucleons are put together. So in part A, we're asked how much energy is released when we form a 4 helium nucleus. And this comes from 2 protons plus 2 neutrons. Now, protons and neutrons don't have any binding energy to start with because they're just individual particles. So what we need to do is look for helium-4 on this graph, which is here, and this tells us that helium-4 has a binding energy of 7 mega electron volts per nucleon. Now in helium-4 there's 4 nucleons, the 2 protons and the 2 neutrons. So this tells us that the binding energy is just equal to the 4 times the 7 mega electron volts, so that's 28 mega electron volts. Now in part B of the question, we're asked how much energy would be released if we assemble iron 56. So we're going to end up with iron, which has 26 protons and 56 nucleons, and we're going to assemble this from 11 helium-4 nuclei and 4 hydrogen-3 nuclei. So there's 4 of these, and we can just check that the numbers add up. Let's check the atomic numbers. 2 times 11 is 22, plus 4 gives us the 26. For helium, we've got 4 times 11, which is 44, plus 4 times 3, which gives us the 56. And so to find the binding energy released, well, we have to do, this is equal to the binding energy of 5626 iron minus the binding energy of the 1142 helium plus the 431 hydrogen. And so this is equal to, now for iron 56, we can read it off here. If we bring a straight line around along there, that is around about 8.75. And we have 56 of those nucleons. And then we have to subtract off these. So with this, this is the helium here. So the helium had 7. And there are 4 times 11 of those nucleons. And now the hydrogen 3, when we read that off the graph, here's the hydrogen 3, so that's around about 2.75 mega electron volts. So that's plus the 2.75, and then there are 3 nucleons in each of those hydrogen atoms, and there are 4 of those hydrogen nucleuses in total. So now we've got just an equation to solve on the calculator. When we type this in, we get 149 mega electron volts. So this is the amount of energy that is released when we form this iron 56 nucleus. So part C says explain why isotopes with A less than 56, so that's down here, tend to undergo fusion, while isotopes up here tend to undergo fission. Well, fusion is when they come together. So these ones which are lighter than iron, if they fuse together, they will enter a lower energy state, they'll release more binding energy, and everything in nature wants to try and get to the lowest energy state it can. So atoms, let's not call them atoms, let's call them nuclei. Nuclei with A less than 56 can release energy by undergoing fusion, which is sticking together. And then these ones up here release energy by becoming smaller, so by fissioning or breaking apart. Nuclei and systems tend to the lowest energy state. So that is why it occurs. Problem 3. In this problem, we're told that a common nuclear decay in nuclear power plants is 10N plus 23592 uranium going to, well, this forms 23692 uranium, which is unstable, and then can decay into 14356 barium and 9136 krypton plus 2 neutrons. And we're told that the mass of uranium-235 is 235.0439 atomic mass units. The mass of barium is equal to 142.9206 atomic mass units, and the mass of krypton is equal to 90.9234 atomic mass units. And in part A, we're asked how much mass is lost during this decay. So the mass loss is equal to the mass that we start with, so the mass of, let's call them the reactants, minus the mass that we end up with, so the mass of the products. So this is equal to the mass of 10 nitrogen plus 235.92 uranium minus the mass of 143.56 barium plus 91.36 krypton plus 210 neutrons. Now this neutron will cancel out one of these neutrons here. So now we can just substitute everything in. We've got 235.0439 atomic mass units minus 142.9206 atomic mass units minus the krypton, which is 90.9234 atomic mass units. Now we have to subtract off the mass of the neutron. We're given that at the front of the tutorial problems as 1.675 times 10 to the minus 27 kilograms. To get that into atomic mass units, we need to divide it by one atomic mass unit, which is 1.661 times 10 to the minus 27 kilograms. So the 10 to the minus 27 will cancel each other out. And then solving this thing on the calculator, we end up with 0.01915 atomic mass units. We can also present it in kilograms. If we times it by 1.661 times 10 to the minus 27 kilograms, we will convert that into kilograms. So we could also give it as 3.180 times 10 to the minus 28 kilograms. And now in part B, we're asked to calculate the amount of energy released. So this is just going to be mc squared, where m is the mass lost, so that's this. 3.180 times 10 to the minus 28 times 3.00 times 10 to the 8 squared gives us an answer of 2.86 times 10 to the minus 11 joules. And we can convert this into electron volts if we want by dividing by 1.602 times 10 to the minus 19. So this is equal to 1.79 times 10 to the 8 electron volts, or 179 electron volts. Now part C of the question says that another possibility is that uranium-235 becomes barium-141 and krypton-92, and we need to write the equation for this. So we've got the same on the left hand side, 10 nitrogen plus 235 92 uranium becomes the 236 92 uranium. And then this decays, but now we're getting 141 56 barium plus 92 36 krypton. And now we need to work out what happens to the neutrons. So on the left, we can see that 92 plus 0 is remains at 92. 56 plus 36 is 92. So the atomic numbers are all balanced. We need to work out the mass number. On this side it's 236. On this side we've got 141 plus 92. That is equal to 233. So we need another 3 neutrons. So this is plus 310 neutrons. So this is a bit of a mess, but that's our equation there. All balanced now. So if we get these products, we end up with 3 neutrons. So then it asks us is which one's more likely to cause a chain reaction and why. Well, the answer is this one. So 141 Ba 92 plus 92 krypton is more likely to cause the chain reaction because it releases more neutrons, and the more neutrons that get released, the more reactions that this can start, because this can now start 3 reactions, whereas this one up here could only start 2 reactions. So this one is more likely to start a chain reaction. Okay, so this is problem 4, where we're asked to write down the equations for some of these reactions. So the first ones are all undergoing alpha decay. So this means that they're all releasing a helium nuclei. Okay, so the first one is polonium-211. And we're told that this undergoes an alpha decay, so we've got 4,2 helium here. Now what we need to do is just calculate the mass numbers and atomic numbers. So atomic numbers on this right hand side have to equal the left hand side. On the left hand side we've got 84. On the right hand side so far we've got 2. So 2 from 84 gives us 82. With the mass numbers, we've got 211 on the left and 4 on the right. So 4 from 211 gives us 207. So then we look up 82 on the periodic table to find out what element that is, and number 82 is lead. So we write down Pb to symbolize lead. Okay, the second alpha decay is 242 uranium, and uranium's atomic number is 92. So again, this undergoes an alpha decay. So we're just balancing our atomic and our mass numbers. So 92 minus 2 gives us 90 protons. 242 minus 4 gives us 238 nucleons. And so then looking up what element number 90 is on the periodic table, it is thorium. Okay, part B, we've now got beta minus decay. So in this case, so beta minus decay, which means that we're releasing an electron from the nucleus. So first of all, we're looking at boron 14. Okay, so this goes to 0 minus 1 e. This is our electron here. Now we balance the mass numbers, so the atomic numbers. So on the right hand side we've currently got minus 1, and on the left hand side 5. So 5 plus 1 gives us 6. With the mass numbers we've got 14 on the left, so we need 14 on the right. Element number 6 is carbon. Now the other thing that happens when we release an electron from a nucleus is that we also release an anti-electron neutrino. So that's got the symbol nu with a little subscript e to show that it's an electron, with a bar over the top to show that it's the antiparticle of this electron neutrino. So we'll be learning more about why this happens in the standard model topic. Okay, next beta negative decay is our osmium 191. So we've got 76 protons there, and beta minus decay again. So 76 plus 1 gives us 77, 191 plus 0, still 191. When we look up what element 77 is, it's iridium. And then we've also got our anti-electron neutrino released. Part C then asks us for beta plus decay. In beta plus decay, an positron is released, which is the antiparticle of the electron. So in this case we've got nitrogen 13, and it's undergoing a beta plus decay. Sorry, that shouldn't be an arrow, we should have a plus. So 7 minus 1 gives us 6, and then we've got 13. Looking up 6, it's carbon, and then because we've got an anti-electron released in this case, we actually have an electron neutrino released in this case. So this isn't the antiparticle, so we don't put a little bar over the top. And then our final reaction is bismuth 207, and it's got an atomic number of 83. Once again, it's emitting a positron. Now 83 minus 1 gives us 82, and then we've still got 207 nucleons. 82 is lead, and then because it's releasing a positron, which is an anti-electron, we also get an electron neutrino released. Problem 5. So we're told that gold 198 has a half-life of 2.69 days. And it's used in cancer therapy, and we have an initial mass, so the initial amount present is 0.500 grams. Then in part A, we're asked how much remains after 4 half-lives. So the amount remaining is equal to the initial amount times a half to the power of the number of half-lives. As each half-life, half of it disappears. So we've got 0.500 grams times a half, and then it's 4 half-lives, so this half is to the power of 4. And so solving that one on the calculator, we end up with this is equal to 0.031 grams. Now, part B asks us what is the decay constant lambda equal to for this reaction? Well, we know that the half-life is related to the decay constant through log 2 divided by the decay constant is equal to the half-life. So this, just rearranging this, tells us that the decay constant is equal to log 2 divided by the half-life. So if we want this in per day, then we've got log 2 over 2.69, and solving that on the calculator, we get 0.258 inverse day. The other option is we could get this into inverse seconds, so we do log 2 divided by this time in seconds, should be 2.69, that's the number of days, times 24, there's 24 hours in a day, times 60 times 60. So this converts it into hours. Sorry, this one converts it into hours, this is into minutes, and this converts it into seconds. And so solving this one on the calculator, we end up with 2.98 times 10 to the minus 6 inverse seconds. Now part C asks us after what length of time will only 0.010 grams be remaining? Well, our equation to describe the amount remaining is the amount remaining is equal to the initial amount times e to the minus lambda t, which is what we use this decay constant for. So we want to have 0.010 grams, and we start with 0.500 grams, and this is e to the minus, let's get our time in days to start with, so that's 0.258 t, and this time is in days, and so we divide this by this, and we end up with 0.020 is equal to e to minus 0.258 t, and now we're going to need to take the natural logarithm of both sides in order to get rid of this exponential. So doing that gives us log of 0.020 is equal to minus 0.258 t, and so t is equal to 15.2 days. Now if we wanted to do it in seconds, we would use this decay constant here instead. So this goes down here instead, and then our answer would be in seconds. If we do that, then we end up with the time in seconds being 1.31 times 10 to the 6 seconds. But this number, 15 days, is probably a lot easier to visualize. Problem 6. This problem says food irradiation is a process in which food is bombarded with nuclear radiation in order to kill off microorganisms. A. Refer to the properties of alpha, beta, and gamma radiation to describe which would be the most appropriate for this process. Well, for this process, we're going to want to use gamma radiation as it's got the most penetrating power. Alpha radiation probably wouldn't even get through the packaging, and beta radiation would be stopped within centimeters of entering, so there's no way that it would irradiate all the food. So let's write that down. Alpha radiation has very low penetrating power, and so would not pass through the packaging. Beta radiation would only penetrate the very top of the food. So gamma radiation is the most appropriate. Now part B says, would this make the food radioactive? Well, no, it would not, because gamma rays can't actually knock protons or neutrons out of the nucleus. And so as we can't change the nucleus, we can't make it become radioactive. So this is another reason for using gamma radiation. If you were using alpha radiation, if it could penetrate, then it can change the nucleus and it could make it radioactive. So no, gamma radiation can not knock protons and neutrons. So we should say all neutrons out of the nucleus. So it cannot cause food to become radioactive. And then part C says, could irradiating the food do anything other than kill off the bacteria? Well, yes it can, because gamma radiation, yes it can. Gamma radiation can affect the electrons, which are around the atoms. It can knock the electrons out because it does have a low ionizing power, and so this can affect the chemistry that is involved, and so it can change the molecules. So let's write that down. Yes, gamma radiation can ionize atoms and affect the chemistry. This is why it is only permitted for some food items in Australia. So Australia has fairly strict rules about the irradiation of food. Some countries allow it a lot more, but in Australia they want to hold off on allowing it until there's a lot of evidence that it is very safe. And it is possible that it may affect the chemistry. Okay, this is problem 7. Okay, so in this problem we've got the thermal neutron, which is absorbed by a 238 nucleus. So we've got a neutron plus a 238 uranium nucleus, and this undergoes fusion and we end up with a 239 uranium nucleus. Now in this process we have some of the energy transferred from mass energy into the resulting oscillations of the nucleus. So what we want to know is how much mass is lost, and then once we know this, we know that this lost mass is converted into energy. Okay, so to work out the mass loss, what we can do is the initial mass minus the final mass. So do m initial minus m final. So the initial mass, we've got a neutron there, so that is 1.008664 U, plus we've got the uranium-238, which has a mass of 238.050782 U, so that is the initial mass, and then we subtract off the final mass, which is 239.054287 U. Okay, so putting this into the calculator, we end up with 5.159 times 10 to the minus 13 U, the U's atomic mass units. Okay, so let's convert this into kilograms, and so to convert it into kilograms we do 5.159 times 10 to the minus 13 times 1.661 times 10 to the minus 27, and we end up with 6.57 times 10 to the minus 40 kilograms. Okay, now to convert this into an energy, we use E is equal to mc squared. So this is equal to 6.57 times 10 to the minus 40 times 3 times 10 to the 8 squared. Solving this, we end up with 7.172 times 10 to the minus 13 joules. We can then divide by E, 1.602 times 10 to the minus 19, and we get 4.81 times 10 to the 6 electron volts, which we can write as 4.81 mega electron volts. So this is how much energy gets converted into oscillation energy in that uranium nucleus. So it's worth noting that the question specified that this had very little kinetic energy for two reasons. One, if it was moving very quickly, it would not have stuck to this uranium nucleus in the first place. The second reason being that if it had a lot of kinetic energy and it did end up sticking to it, then we'd have to include that energy into the total energy as well. And so that would increase the energy of the oscillations.